Hello, everyone. It's a pleasure to have Ashwin Sah from MIT as a speaker today. He will talk on popular differences for matrix patterns. As usual, we will have questions at the end. If you have questions during the talk, please feel free to write in the chat and we'll try to raise it to Ashwin. Otherwise, at the end, there will also be an unrecorded informal discussion. Well, Ashwin, you can start.
Thanks for the introduction. So before I begin, this work is joint with Aaron Berger, Mathbb Sani, and Jonathan Tudor, who are also from MIT. Okay. So let me just recall Semreti's theorem, or rather a specific variant of Semreti's theorem, which is only true, as it turns out, for 3-term arithmetic progressions and 4-term arithmetic progressions. So suppose that we have a subset of the first n integers, which has positive density. Semreti's theorem tells us that there is some k-term arithmetic progression inside of the set. And you might ask for more. You might wonder how many such progressions are there. And it's pretty easy to see that for a random set, you should expect there to be around not quite alpha cubed n squared arithmetic progressions just because of overflow errors, but on the order of alpha cubed arithmetic progressions. And as it turns out, one cannot quite guarantee that for a general dense set, but one can guarantee the following, which is a result of green for 3 APs and a result of green tau for 4 APs. So what you can guarantee is that given a dense set of density alpha, then there is some difference d not equal to 0, such that the number of 3 APs with difference d in your set is at least around alpha cubed times n. So this sort of matches what you'd expect from a random or maybe quasi-random set. And similarly, there is some d such that the number of 4 APs with difference d is at least around alpha to the 4 times n. And in fact, you can find many such differences. So one sort of way of thinking about this is not only does Semreti hold, but you can also find sort of a popular difference where there are many arithmetic progressions. In fact, sort of at least the right amount, and maybe even more. As you can see, for example, if A is just alpha n consecutive integers, then you'll actually expect much more than alpha cubed. You'd expect around alpha. But in general, for a random set, you'd expect alpha cubed, or alpha to the 4, or alpha to the k in general. So as I briefly mentioned, this is false when k is at least 5 due to a construction of Ruja. And actually, you can get nowhere near alpha to the 5th many, as it'll turn out. It ends up being it ends up decaying super polynomial. And I'll just mention that there is sort of a natural ergodic theory parallel about this result. And it has to do with looking at the multiple recurrence set that shows up in Semreti's theorem stated ergodically, and looking at when the measure is large. And one can show something about the syntacticity of this different set. Although I won't really talk too much about the ergodic theory language here, just to point out that unlike Semreti's theorem and Furstenberg's correspondence, there's not exactly a direct correspondence for this type of more refined problem when talking about Semreti's theorem. Okay, so here's sort of the basic result. Maybe an initial question you might have, which I briefly addressed, was why is it necessary to find a specific difference that has this property? So I briefly discussed this, but just to be very explicit about this, it turns out that a blowup of Behrens construction gives you dense sets in Z of size, say, alpha n, which has an amount of 3 APs which actually decays faster than any polynomial, so much less than alpha cubed. However, despite these Baron style constructions, such that only a certain amount of APs can actually be present, if you restrict to specific differences which sort of see the structure of that construction, then you're able to do better all the way up to around alpha cubed, according to this result. I think that should say n squared, but. So these initial results imply that for k in 3 and 4, you have sort of a popular difference result, but when k is at least 5, you don't. So one might ask more generally which patterns satisfy this property and which patterns do not. So just to ease our discussion of this problem, I'll give sort of a small bit of notation. So this is, for now, we're just going to address patterns that have so-called affine dimension 1. So for example, 3 APs and 4 APs are an example of this. But let's allow patterns in potentially any number of ambient dimensions, so up to R. So R equals 1 corresponds to the usual setting of Semiretti's theorem, while R equals 2, for example, contains patterns such as axis-aligned squares, where you can basically translate around a square in Z2 of any potential side length, but it's axis-aligned. And that would correspond to a pattern of size 4 with the points 0, 0, 0, 1, 1, 0, 1, 1. And as you can see, when A varies over Z to the R, A plus D times that, D times P for P in your pattern set would correspond precisely to the 4 corners of an axis-aligned square. And similarly, if you remove that last corner of an axis-aligned square and you only look at the first 3 corners, then you get a pattern which is sometimes called a corner. So this is sort of a natural class of patterns that one might discuss with regards to Semiretti's theorem and multidimensional Semiretti. And just to sort of establish the bit of notation that we want to use, given some finite set in Z to the R, which cuts out one of these patterns, let's define PDD sub P of alpha, so popular difference density, to be the maximum real number such that as long as we have a dense set of density at least alpha, then we have some difference which is at least PDD popular. So just to be very explicit about this, if we count the number of starting points such that the entire pattern, when scaled by D, is in our set, then you have at least PDD times n to the R many starting points. So the results from earlier of green and green tau did this in R equals 1 with P equals 0, 1, 2 or 0, 1, 2, 3. And they were actually able to show that this PDD value was equal to alpha to the power of the size of P, which is, you can convince yourself the best you could hope for by basically taking a random set. Okay. So one quick note is that this is actually always a positive real number. You can always find some positive density of basically arithmetic progressions in your set of a certain difference even. And this follows due to the multidimensional Semiretti theorem, along with a sampling trick that dates back to Varnavides. So it's not really interesting to ask, does this thing exist? It does. But it's interesting to ask what its behavior is. And as I mentioned, a quasi-random set or a random set will have this value equal to alpha to the power of the size of the pattern, because all of the elements of the pattern will look random with respect to each other. So you can't do better than that. So you could first of all ask which patterns are alpha to the P on the nose. And secondly, you can ask which patterns decay polynomially. Those are sort of the interesting questions you can ask about this. And as I mentioned, just sort of to exercise the notation, the PDD of 0, 1, ... k minus 1 corresponds to asking this problem for k APs. And when k is almost 4, we know it's alpha to the k. The case k equals 2 is a simple Fourier computation. And for k is at least 5, due to Ruja, it decays super polynomially. And it turns out that if you just modify Green's argument, then not only is this true for 3 APs, but if you want to look at sort of any size 3 pattern on the line, all of them actually have alpha to the 3. And the Green Tau result, which shows it for 4 APs, actually holds for patterns that look like 0, A, B, A plus B. So for example, if A is 1 and 3 is 4, and B is 3, then you get 0, 1, 3, 4. And this pattern corresponds to the first 2 and last 2 elements of a 5 AP. And counting those patterns, according to Green Tau, also satisfies that you can always find a popular difference. Okay. So now let's move on to more complicated patterns in higher dimensions. So first of all, for the corners case, which I mentioned, we have affine translated squares and we have corners, which is the square minus the single point in the top right. So work of first Mendash, and then Fox, myself, Sani, Stoner, and Zhao, and then Berger, building on each other in this order, showed that this popular difference density for corners, which is explicitly represented by this pattern, A plus D times these 3 points, is the solution to a variational problem, first of all. And it turns out that the solution to this variational problem grows roughly as alpha to the 4th, but actually it's not exactly alpha to the 4th. So the right exponent is 4, but it's off by some amount, which basically is fundamentally related to the best bounds for the triangle removal lemma. So I won't go into what exactly this function is, but other than that, it's related to those sorts of constructions. And going further, work of myself, Sani, and Zhao in more recently actually fully classifies which patterns of affine dimension 1, so the patterns that we're looking at so far, which ones have this precise equality, which ones actually satisfy a popular difference in sort of the quasi-random sense. As it turns out, all patterns of size at least 5 are super polynomially bad. And furthermore, we work towards a classification of which such popular difference densities have polynomial growth, although there are still a few outstanding questions. And with regards to polynomial growth, those outstanding cases involve 4-point patterns over the integers, as well as 4-point patterns in Z2 that are in convex position. So for example, this case of squares that I mentioned, affine squares, those 4 points in the pattern are convex. And so that's a case where we know that it is not exactly alpha to the P or alpha to the 4, but actually we can show it's around at most alpha to the 5, but it's not clear whether it's supposed to be a polynomial growth or not. Okay, so just to summarize what we've done so far, we've talked about the popular difference problem, first for Semorati's theorem, and then for more general patterns, where we have a pattern in some amount of dimensions that's defined by a single scaling sort of invariant. So for example, squares, where you have a single side length, which determines how big to scale the pattern up, and that's it. So one could ask, what about patterns that have potentially multiple parameters defining it? For example, the most simple case you would imagine is rotated corners or rotated squares. So here, no longer do we need the axes of, say, the square to be axis aligned, but we could potentially rotate the square and embed it somehow into the integer lattice. So there are many squares on lattice points that don't quite have that do have integer coordinates but are not axis aligned. So you could ask, what about those? Or what about rotated corners? Unlike Samaretti, where you're just asking for the existence of a pattern, and therefore the non-rotated version implies the rotated version, since here we're counting the amount of corners or rotated corners that appear in your set, there's actually no obvious equivalence between the two cases. So it's not like one is easier than the other or anything like that. Although, as it turns out, this rotated setting will be slightly easier to understand. So just to be very explicit about what these patterns look like, you can think of these as being in Z2, and we can represent those as, say, vectors. So we have x, y, that's the base of our pattern. And let's say the difference is AB. And we have xy, the base. We have xy plus AB, which is the first leg of the corner. And then the second leg is going to be the same vector added to the point, except we have to rotate it by 90 degrees counterclockwise. And that corresponds to applying this matrix, this rotation matrix, 0, -1, 1, 0 to it. This forms that pattern. So you can see this invokes a very natural notion of matrix patterns now. So now I'll define patterns, or give sort of one way to define patterns that are in affine dimension at most k now, and ambient dimension r. So earlier we were just talking about affine dimension 1. So now instead of just r-dimensional points, which are being scaled up and down by a single difference parameter, the natural notion is r by k matrices. So we have some finite set of r by k matrices. And again, we define PDDP to be, this number such that if I have a set in r dimensions, then there is some difference of vector d in k dimensions, non-zero, such that this pattern is always inside of our set. And this happens at least PDDP of alpha times n to the r times. So it's the exact same definition. And as before, you would expect, if I have a random set, then this number really could be taken to be alpha to the power of the size of the pattern by the same sort of concentration arguments as you would always use. And the question is, for these matrix patterns, such as this pattern above, which looks like 0, identity matrix, and this rotation matrix, for patterns such as those, is it true that you can get alpha cubed? Or if not, then what is the precise behavior? Of course, we know Samaretti's theorem holds. So again, this Varnavides trick can show that this PDD is always positive. So it's really a question of what is its behavior. Okay. So one technical point about this definition, which might not be completely obvious immediately, is really I should say this is affine dimension at most k. Just the reason being that, you could have a certain collection of matrices where I think the right condition is their common null space has some vector in it, something like that, where basically secretly we're just collapsing dimensions in the vector d secretly. And you don't necessarily see it if you just say, oh, well, it's in k dimensions. But secretly, it's actually, a lower dimensional pattern. So I don't really want to get into the details of, what's a affine dimension exactly supposed to be defined as. Most of the matrices that we're going to be working with are going to be, actually all of them are going to be full rank. And in fact, we're only going to really be dealing with the setting where k equals r. And we have full rank matrices. And so then there's really no question. It's going to be in dimension k equals r. Okay. So this sort of concludes the introductory portion where I talk about the definitions. So feel free to jump in and ask any questions to clarify, the notions that have been introduced. If not, I'm going to move on to talking about some results. this here is really the most important definition. It's really just saying how many times can I have this pattern of a specific difference if I'm in a dense set. So maybe just to be explain a little further, for example, in the case of rotated corners, I would have a set of density alpha, and I'd want to find a popular difference a comma b, such that there are many such xy, such that if I go by ab and then I go by its rotation, all of that is in the set. And I'd want maybe alpha cubed times n squared, many such xy, satisfying that for some non-zero ab. And as it turns out, we'll be able to do that. So let me move on to talking about what has been asked and what we can do with these matrix patterns. So first of all, this sort of natural question for corners and popular differences for corners was actually asked by Ackelsberg, Bergelson, and Best. They mostly were focusing on ergodic theory, but they had some combinatorial conjectures as well as some ergodic conjectures which have combinatorial analogs in this popular difference setting. And just rephrasing what their conjecture was in our own notation, they were basically asking that whether the popular difference density of this corners pattern, which is these three matrices, is alpha cubed. So matching a random set. So our first result is that yes, this is true. And in fact, this is true in more generality. So if we have r-dimensional matrices, and so as mentioned, you really want these matrices to be non-singular, or at least not to share a null space. But if they're non-singular and if their difference is also non-singular, which is a technical condition, then this popular difference density of whatever matrix pattern you get out is going to be alpha cubed. So these more general patterns aren't necessarily the same as just rotating a pattern. You can actually have more general things because sort of the patterns corresponding to rotating a pattern kind of are coming from orthogonal matrices that have rational coefficients. But you can have more general things that sort of more look like certain affine types of shifts. But I'm not going to get too much into the geometry of this. So we're able to prove this in a large amount of generality for these 3-point matrix patterns. And I'll just mention that for the rotated corners case, which was asked by Ackelsberg, Bergelson, Best, this was actually independently resolved by Kovacs. Now, I'm not going to state the actual conjecture of Ackelsberg, Bergelson, and Best, but with regards to 4-point patterns, they made a conjecture which sort of you can see as an ergodic theory analog of the following conjecture, which is that if M1 and M2 are matrices and they're invertible and their sum and difference are invertible, then the popular difference density of alpha is equal to alpha to the fourth. This is basically the analog of what they conjectured. Although, again, there's not quite an exact equivalence anymore. So with regards to this conjecture, you might ask, okay, so why these 4 things? And the reason has to do with this result of green tau that we briefly mentioned earlier, where if you have a linear pattern of the form 0, A, B, A plus B, then you get alpha to the fourth. And as it turns out, if you look at 4-point linear patterns, those are the only ones which give you alpha to the fourth. And the reason has to do with some magic positivity identity, which I don't want to go into yet. But basically, it means that the natural 4-point patterns that you'd expect to have a popular difference are really going to be these types of patterns: 0, A, B, A plus B, and now with matrices instead. So these are the matrices that they want to look at, these patterns, and based on this linear behavior, for example, for APs, Semreti's theorem, it's very plausible that you have this alpha to the fourth popular difference density. So what we show is that this is true over fp to the n, so in the finite field model for odd primes, as long as you have one additional condition, which is that m1, m2 inverse has no pair of eigenvalues that are equal to negatives of each other. So here, okay, given a matrix over fp, you can find its characteristic polynomial and find its eigenvalues over fp bar, the algebraic closure. And we want no pair of those eigenvalues to be negatives of each other. And if that holds, then we can prove the desired result. So here's sort of a more technical statement of that. Basically, if you have k by k matrices over fp, and I have a dense subset of fp to the n, k tuples of that, then I have lots of my pattern with some non-zero difference. So I don't want to say too much about the formal statement, but one sort of thing that I should clarify, just so we don't get confused about these d-dimensional or k-dimensional patterns, is how to interpret what M1 applied to D means. So earlier, there was sort of a very natural way in which we could represent these corners, these rotated corners, as a vector plus a matrix applied to a vector. And here we should just be a little bit careful, because elements of fp to the n are already vectors. And then I'm taking it to the kth power. I'm looking at k tuples of that. And so then, you start to get a little confused. So one way to sort of untangle this is think of fp to the power of n as an underlying group G. And okay, in this particular case, we're looking at the finite field model. And now think of a dense subset of G to the power of K. And now we also have some K by K matrices. And now X and D are going to be in G to the power of K. They're just K tuples of elements of our group G. And you can apply a matrix M1, which is K by K, let's say over FP, in a very natural way to a vector of size K, just by usual matrix multiplication. And then in this particular case, the fact that our group G has order or has exponent P implies that these matrices can actually be defined over FP. There's another way to look at this where you represent X and D. You represent the points of our underlying group as like matrices, but I think this statement is good enough for our purposes. So you might be wondering while I was explaining that, why do we have this extra sort of very strange condition? I mean, a priori, this is just some pattern. In the one-dimensional case, you could just say, oh, 0, A, B, A plus B, it always works. So you'd say, okay, a similar thing should work in general with these matrices. But all of a sudden, you have this weird spectral condition showing up. And of course, the natural question that you might ask is, okay, so do you actually need this spectral condition? Why do you need it if you need it, and do you even need it? It seems a little strange at first. So we actually show that there is a counterexample when you have a pair of negated eigenvalues. So just to be clear, this isn't technically a counterexample to the original ergodic conjecture of Ackelsberg, Bergelson, and Best, because it's not a direct transference. But it certainly suggests that their counterexample, or that their conjecture, needs some extra spectral condition analogous to what we have discovered in the combinatorial model. So as it turns out, the pattern for rotated squares, if you just write down the matrices that you get, this M1, M2 inverse quantity will actually have a pair of negated eigenvalues equal to the square root of -1 and the negative square root of -1. And over F5, the square root of -1 is actually 2. So it'll have a pair of negated eigenvalues 2 and -2. And just to be very explicit about what we prove, we show that I have some density alpha, then I can find a set in F5 to the n squared, so G squared, where G is F5 to the n, such that for any non-zero difference, AB in G squared, if you look at the number of rotated squares that are rooted at some point, xy, so you can see this is the point plus the difference, this is the point plus the rotated difference, and this is the fourth point of the square. The total amount is always at most 1 minus c times alpha to the 4 when alpha is sufficiently small. You can always find a set like this. So this shows that the popular difference density over F5 at least is at most 1 minus c times alpha to the 4 in general. Just a little bit worse than quasi-random, but that already suggests that there's more to the picture. Okay. So now for maybe the remaining half of the talk or so, I want to discuss at some amount of detail, hopefully just give some ideas about how these results are proven in general. So I'm going to focus first on how one, at least at a high level, proves this green tau result about 4 APs in Samorati's theorem. And maybe I'll do it over the finite field model for simplicity. We'll talk about that. Maybe briefly also this 3 AP result, which is substantially simpler. And then from there, I'll talk about what you have to do in order to understand these matrix models, and maybe get into what's going on with the spectral condition, why you can do it and why we can do it, let's say over the finite field model for simplicity, when we have this spectral condition that M1, M2 inverse has no pair of negated eigenvalues, but why otherwise you would expect it to be false if you do have a pair. Okay. So now you can think of this as sort of moving on to the third phase of this talk. Okay. So at a high level, the proof strategies for all of these results, all of the proofs of positive results anyways, involve arithmetic regularity. For counterexamples and constructions, there's a lot I could say about it. I'm not really going to talk about that during this talk, but there are a lot of interesting things starting from Roos's counterexample and other things using Barron's construction, certain types of projections, and other very interesting techniques. But that's more of a more varied toolbox that I won't really get into here. On the contrary, all of the positive results use arithmetic regularity. So when the pattern size is 3, you can just think of it as regular arithmetic regularity for U2. So this is basically Green's arithmetic regularity lemma for like 3 APs and abelian groups and stuff like that. And the 4-point pattern proofs for the positive results that are proven all use U3 regularity. Okay. So I'm not going to state the U2 regularity stuff. It's strictly easier. It's kind of like Samorati's regularity lemma. Let me just state U3 regularity, U3 arithmetic regularity. So here's a bunch of words. So I'll just say what sort of the idea behind arithmetic regularity is. If you want, you can try to parse all of this, but let me just explain it. So the idea is given a function f over z, or I'll just do fpn for simplicity because I don't want to talk about null sequences. You want to understand, say, its arithmetic properties. For example, I want to understand its 4 AP counts or stuff like that. It's pretty well known in this field of additive combinatorics that if you use this Gowers-Cauchy-Schwarz method, you can reduce this 4 AP control to control of the Gowers U3 norm. And in general, for KAPs, you can reduce to the UK minus 1 norm. And that sort of controls the arithmetic structure of our function f. And so then a big question is, okay, what sorts of functions are small or large in this Gowers norm is a question that one could ask, which has been studied extensively. And another question you could ask is, given that everything is controlled by this norm, if I change my function by a small error term in the Gowers norm, that shouldn't change the 4AP density by very much, or any other property, dense property about these 4APs. So given that fact, can I sort of find a nice set of models for my functions, which basically look the same, and you can prove look the same with regards to any statistic that you'd care about, but which is a model of finite complexity rather than a complexity that grows with, you know, the group size. So FPN, n is growing. And it turns out that you can do this. And this is the content of arithmetic regularity, which should be viewed in analogy with semi-regularity lemma, or hypergraph regularity for higher regularities. Okay, so at a high level, what it does is it decomposes our function f into a structured component, which you can think of as our finite complexity model of our function, something that's small in L2, and something that is pseudo-random, in the sense that it has a small U3 norm. And so as mentioned, that won't really affect anything with regards to the 4AP density or anything else, but by this Gowers-Cauchy-Schwarz argument. And as it turns out, this structured component is merely, at least in the finite field model, you can take it to equal a certain conditional expectation. So what that means is you can basically look at some finite amount of information about, let's say, our input vector x in FPN, and then output some function of that finite amount of information. And in fact, I can tell you what that information is. So here B1, I have a quadratic, what's called a quadratic factor, and all you really need to know is B1 is a list of vectors which define linear forms, and B2 is some bounded list of quadratic forms, so matrices. And what I do is, given an input value x to compute f structured, what I do is I compute what every vector in B1 dot producted with x is, and I compute what x transpose mx is for every quadratic form m in B2. I compute that finite list of numbers, and then I plug it into some function. That's going to be my structured component. That's going to tell me everything I wanted to know about the arithmetic structure. Okay, and then I have something that's small in L2, which won't matter. And I'll have something that's pseudo-random, which, as mentioned, will not perturb this arithmetic structure by very much. And then I also, want to preserve one boundedness and some other stuff. The key point, as I mentioned, is that, like in semi-regularity lemma, I can find a model that has bounded complexity. If I fix some error terms beforehand that I want to say, okay, I want to be this good, then I can find some bounded complexity to go along with it. And as it turns out, it'll be convenient to know that the quadratic forms that are defining our information are all of high rank, and in some sense high rank with respect to each other. That's more of a technical condition, but it makes the analysis that comes out of this regularity lemma really nice. Whereas otherwise, there are sort of, you can still do it, but there's some difficulties. You can think of this as really refining the amount of information you present so that it's presented in the simplest form in a very decoupled manner, rather than having weird dependencies between the different quadratic forms that show up. Okay, so this is a long statement, but sort of the takeaway is, given a function, and I want to understand its 4AP structure or something about its U3 structure, then I can basically replace it with something that depends on a finite amount of linear forms and a finite amount of quadratic forms in my variable. That is, we can sort of reduce to model behavior, which just looks linear and maybe also quadratic, or quadratic in some sense, because over the integers, quadratic means there are a couple of things that look quadratic that don't quite immediately appear like a quadratic. But we'll focus on the finite field model here as it is easier to think about. Okay. So as mentioned, a quadratic factor has this list of linear forms, and this list of quadratic forms satisfying, some rank condition, let's say. And it allows us to replace our function by a structured model function, which, okay, so I've been saying this in words, but explicitly, we can replace our function f by basically something that depends on these dot products and these quadratic form outlets. And okay, so this rank condition is really telling us that as the group size goes to infinity, if you look at, the different values of x that can arise, and you look at what b1 of x and b2 of x are equal to, which I'll just denote as these sort of tuples, then they actually equidistribute over fp to the l plus n. And this is what the high rank condition buys you, because if m1 is something that's very low rank, then it's not going to look like it equidistributes for sort of technical reasons, because it really looks like a bunch of linear behavior, finite amount of linear behavior, rather than something genuinely quadratic. So you have this equidistribution. And in fact, if you look at some x and some d, let's say x and d are ranging over the whole group or over finite codimension subspaces, then you'll find that if I look at what happens when I plug in x plus jd over the different values of j that you could have in your pattern, and you vary x and you vary d, then you'll actually have equidistribution on a very large space. So it won't quite be this thing to the power of 4. So I have 4 copies of this vector with different values of the pattern plugged in. However, there are some obvious linear dependencies. For example, there's this equation, which you can think of as the analog of the fact that the third finite difference of the square function is 0. And you can imagine there are similar, actually more equations involving these linear terms when you plug in x, x plus d, x plus 2d, and x plus 3d. But overall, regardless, because I reduced to this finite complexity behavior, I understand it completely. And in this case, I understand it as some equidistribution statement. And so now at this point, I've basically reduced from a general function to basically a function that looks almost quasi-random on some sort of finite dimensional subspace, finite dimensional space in some sense. So we're basically almost done. Modulo a lot of technical arguments that let's ignore. At a very high level, you can show that the fraction of 4 APs, and in fact, the fraction of 4 APs where this first quadratic factor zeroes out the difference by some further modifications, you can show that this quantity actually is approximately equal to this sort of variational problem almost. Sort of the way you see this is it comes directly out of this equidistribution of this sort of 8-fold tuple. What ends up happening is if I condition on the difference being zeroed out by all of the linear equations, then all of these vectors are all equal to each other, but these things are equidistributing given this equation. So as it turns out, through not a very hard calculation, not only can I reduce to this model, but actually this model reduces down even further using our equidistribution. And it's simply a matter of looking at some simplified average of a bivariate function over a finite field. And so explicitly, you look at this expectation over A and B1 or B0, B1, B2, B3, where we condition on this equation being satisfied. And G here has roughly the same expectation as F. And now, as it turns out, because this condition has some symmetry in it, one can actually use Cauchy-Schwarz here and then do some further inequalities. And one can actually show that this right-hand side is at least equal to the expectation of G to the 4th power, which is basically precisely what we wanted. Because at that point, then I can say, well, that means that there was some original difference, D, in the subspace, I guess, such that the average over x of f of x plus d, etc., is at least alpha to the 4. And that's precisely what you want. So you can see this final inequality relating this to the 4th power of the expectation as Cauchy-Schwarz, or you can also view it as a Fourier positivity. But I won't go into that. Anyways, so this is just a very high level. There's sort of this magic symmetry that occurs. So now, with the time I have left, let me briefly talk about, just sort of verbally talk about what happens when you try to extend this to the matrix setting. So as mentioned, we have this magic symmetry property that's required. And this is actually the reason why green tau extends to patterns of the form 0, A, B, A plus B, but not other patterns. And this can also be seen in over the integers with Neal sequences, but I won't worry about that. And in the matrix setting, it's much more complicated, but at a high level, if you work it out, you have equodistribution over some larger spaces that depend on the matrices. And they actually can be realized as a sum of smaller spaces depending on the spectrum and eigen decomposition of this sort of key matrix M1, M2 inverse. There are some issues about definability of FP bar and FP, etc. Let's not address that. And as it turns out, the spectral condition that we imposed, that no pair of eigenvalues are negatives of each other, corresponds to a necessary and sufficient condition for these equodistribution spaces to satisfy a similar magic symmetry condition. This magic symmetry condition will hold generically, but if two eigenvalues are negatives of each other, there can be some magic interference, and it can basically break the symmetry property. As it turns out, it's fine to have repeated eigenvalues, and even sort of Jordan blocks are fine. What's a problem, though, is negated eigenvalues, specifically. And our counterexample for rotated squares in F5 to the n, where we have a pair of negated eigenvalues, corresponds to writing down an explicit function, like an explicit model, as we've discussed, these explicit models, which in some sense exploits the failure of symmetry that's involved. And then there's some massaging you have to do to get it to be a genuine counterexample for all directions, for all differences. But I won't talk more about that. And just in terms of the other sorts of technical things that you need to do, although certainly this spectral condition and understanding this space decomposition are the most important part in terms of interest, one has to show that 4-point matrix patterns are controlled by U3 in order to apply the techniques of arithmetic regularity to begin with. And as it turns out, as long as you have full rank patterns with R equals K, with ambient and affine dimension equal, and they're sufficiently generic, then one can actually apply this Gowers-Cauchy-Schwarz argument. And one also has to write down an appropriate generalized regularity lemma. So now let me just mention some open problems, and then we can be done. So first of all, presumably one can extend these 4-point results, these matrix results, to the integers. But due to the technical nature of some of these matrix arguments, it's not immediately clear that it'll just directly go through, but we imagine that it should go through. So that's one sort of direction. Sort of a more interesting, sort of just genuine open problem is, do rotated squares have popular difference density of some polynomial growth? We showed that it's not exactly alpha to the 4. We showed that it's 1 minus c times alpha to the 4. Is the exponent 4? Is it 100? Or is it super polynomially decaying? Similarly, do axis line squares satisfy this? This is less related to what we've been discussing here, but it's an interesting problem. And as I mentioned, unlike Samaretti's theorem, neither of these imply the other directly, at least a priori. And this latter question I expect to be much more difficult, because arithmetic regularity and Gowers inverse theorems, etc., in the setting of axis line squares is not really understood at all. But for rotated squares, because it is controlled by U3, you could imagine that there is something there that could be studied. And in fact, because of this arithmetic regularity argument, you can still carry out most of the argument from earlier. It's just that at the end of the day, you'll find that you've reduced to some sort of variational problem potentially, although it's not an exact equivalence, but you're reduced to some variational problem where it just is not always at least alpha to the 4. But you can imagine by studying and understanding that variational problem, you might be able to prove that there's a polynomial growth involved or some other type of behavior. So that's sort of an interesting direction to pursue. Great. So you can find this online. Thanks for your attention. Are there any questions or anything else?
Thank you, Ashwin. Let's unmute ourselves and give a round of applause first. Thanks a lot. Questions? Ashwin, I had a question regarding the very first thing you mentioned about this Bergelson construction when you blow it up. So can you explain it a bit more? What happens there?
Yeah, so this was to explain why one needs to look at, specific differences rather than just counting the total number of APs in a set. I mean, to begin with, counting the total number of APs runs into a funny problem where if you do it over the integers, there's sort of an overflow error that can happen. Whereas if you do it over like mod p or something, mod n, it's not immediately obvious that that should exist anymore. Like if you take a random set. So there's already some, question of what exactly is involved there. Yeah, but in terms of this Barron construction, I think, okay, so I don't want to try to do this live, but I think what you can do is you can take a, so Barron's construction tells you that as n grows, the largest density you can have of a 3AP avoiding set decays over time. So let's consider a Barron set of density alpha, which is of maximal size. At some point, you can no longer maintain the density alpha, of course, but up to some point you can. So take that Barron set, and then I think you might even just be able to turn each of those points and blow them up into intervals. But I might be mistaken. And I think yeah, I think that works. You blow them up into intervals of size, whatever it is, so that now the entire set is in an interval of length n. So this is still of density alpha. And what happens is, suppose I have a 3-term arithmetic progression. If I have 3, and okay, maybe you have to add some extra spaces. So I shouldn't replace every point by an interval, but I should only include it in my set like the middle 1/4 of the interval. What's going to happen is if I have a 3-term arithmetic regression between distinct parts, because all of my points in the blown up set are very close to the center, if they form an arithmetic regression, you can show that the original sort of points in the model set also form an arithmetic regression. But we constructed it to avoid 3 APs, so that can't happen. Therefore, the only 3 APs in the entire set are contained within these small intervals. And then if you count them up, you'll get a very small amount because all 3 of them need to be in a very localized manner. And that actually sort of explains why you need to consider a non-zero difference, because this counterexample, although it sort of partitions you into some amount of growing number of parts where each of them looks sort of much more nice, what that's telling you is that if you take a difference, which is constrained to be in that small interval, then all of a sudden things will look much nicer than before. And what this popular difference result is saying is that you can't escape this behavior in some sense. Maybe you can try to avoid it by doing some blowups and some other stuff. But at the end of the day, you'll be able to find some difference somewhere, in fact, many differences that sort of see that blowup structure or see whatever sort of contrived arithmetic structure or arithmetic regularity you see with the set. Yeah.
Yeah,
Oh,
that makes sense. Thanks a lot. Any more questions? Yeah, Jan has a question.
So you had on one of the early slides, you had this node that, what do you call it? PDD is positive.
Mhm.
And yeah, so to me that seemed to follow immediately from Semeradi's theorem. So what is this Varnavides result about? Could you explain that?
Yeah, I mean, this is a pretty old thing. So, back then, these sorts of implications maybe weren't as standard. But I imagine the reason we're saying, yeah, that this follows immediately from Semeradi's theorem is what you can do is you can just, given your set, you can sort of, I think, subsample like a short interval intersected with the set, and then use Semeradi on that shorter interval of finite size. And then you can show with positive probability, you'll actually sample a k-term arithmetic progression by basically subsampling some interval in our set, and then using Semeradi's theorem to guarantee some KAP within that interval, and then just outputting that. And that immediately, this sampling trick immediately shows that this, that not only do I have like one arithmetic progression, but as n goes to infinity, I have, the right amount. And this actually appears, I think, in the context of three-term arithmetic progressions, at least, in this work of Varnavides, where he proves, I think this is the one where he proves Roth's theorem, but I might be mistaken.
Okay. So now I understand. So this was like one versus positive density.
Yeah, it's
okay.
one versus positive density.
Okay.
There is an argument to be made here, but this is something that now is pretty standard in the literature, but I think it's to Varnavides, although I'd appreciate a correction.
Thanks.